In mathematics, a matrix group is a group G consisting of invertible matrices over some field K, usually fixed in advance, with operations of matrix multiplication and inversion. More generally, one can consider n times n matrices over a commutative ring R. A linear group is an abstract group that is isomorphic to a matrix group over a field K, in other words, admitting a faithful, finite-dimensional representation over K. Any finite group is linear, because it can be realized by permutation matrices using Cayley's theorem. Among infinite groups, linear groups form an interesting and tractable class. Examples of groups that are not linear include all sufficiently large groups. For example, the infinite symmetric group of permutations of an infinite set. Basic examples: the set Mr of n times n matrices over a commutative ring R is itself a ring under matrix addition and multiplication. The group of units of Mr is called the general linear group of n times n matrices over the ring R and is denoted GLN or GL. All matrix groups are subgroups of some general linear group. Classical groups. Some particularly interesting matrix groups are the so-called classical groups. When the ring of coefficients of the matrix group is the real numbers, these groups are the classical Lie groups. When the underlying ring is a finite field, the classical groups are groups of Lie type. These groups play an important role in the classification of finite simple groups. Finite groups as matrix groups. Every finite group is isomorphic to some matrix group. This is similar to Cayley's theorem, which states that every finite group is isomorphic to some permutation group. Since the isomorphism property is transitive, one need only consider how to form a matrix group from a permutation group. Let G be a permutation group on n points and let G1, Gk be a generating set for G. The general linear group GLN of n times n matrices over the complex numbers acts naturally on the vector space Cn. Let B equals B1, Bn be the standard basis for Cn. For each G, let me in GLN be the matrix which sends each Bj to Bgi. That is, if the permutation G sends the point J to K, then me sends the basis vector Bj to Bk. Let M be the subgroup of GLN generated by M1, Mk. The action of G on omega is then precisely the same as the action of M on B. It can be proved that the function taking each G to me extends to an isomorphism, and thus every group is isomorphic to a matrix group. Note that the field is irrelevant since M contains only elements with entries 0 or 1. One can just as easily perform the construction for an arbitrary field since the elements 0 and 1 exist in every field. As an example, let G equals S3, the symmetric group on 3 points. Let G1 equals and G2 equals. Then M1 B1 equals B2, M1 B2 equals B3 and M1 B3 equals B1. Likewise, M2 B1 equals B2, M2 B2 equals B1 and M2 B3 equals B3. Representation theory and character theory. Linear transformations and matrices are well understood objects in mathematics and have been used extensively in the study of groups. In particular, representation theory studies homomorphisms from a group into a matrix group, and character theory studies homomorphisms from a group into a field given by the trace of a representation. Examples: see Table of Lie groups, list of finite simple groups, and list of simple Lie groups for many examples. See list of transitive finite linear groups. In 2000, a long-standing conjecture was resolved when it was shown that the braid groups Bn are linear for all n.